Let's get back to our documentation phase where we will explain through our formulas and our document. Now let's talk about convective flux. We have seen that convective flux is all about bulk motion. So we know that in this formula there will be a term with associated velocity. But here we will not talk about simple velocity. It will be a characteristic velocity.
Okay, now let's learn more about what the characteristic velocity actually is. Think of characteristic velocity as an average speed of a process in a system. Imagine you are watching cars on a road. Instead of tracking every single car, you pick one number of car that tells you roughly how fast most of the cars are going. In chemical engineering, when we study how things like heat, chemicals, or energy move around, we use characteristic velocity to represent that typical speed. It helps us to design the system like pipes or reactor, so everything moves around it predictable and manageable easily.
Let me simplify it even more. Imagine you are blowing air through a straw. The speed at which the air moves through the narrow part of the straw is like characteristic velocity. It tells us how fast things flow in a system. In chemical engineering, we use it to understand how fluids, heat, or chemicals move through pipes or reactors efficiently. It helps engineers design better systems for making products safely and quickly.
Exactly.
I think now they have got the
What
idea
the
of characteristic velocity is. Now, the formula of convective flux will be similarly like that, something like that, quantity per unit volume into characteristic velocity.
Exactly.
So, as we have talked about that, different components will have their different property in convective flux. So,
Similarly, for multi-component system, characteristic velocity will also changes as the summation of individual velocity of each component is summed as the total characteristic velocity, which is equals to summation of bi vi
beta I into Vi.
So
So basically, beta I is the weighting factor, and Vi is the velocity of a constituent. So since each constituent will have its like individual velocity and will have its individual beta I. Here, you can see that the characteristic velocity for mass average, molar average, the weighting factor can be for mass average it will be mass fraction, for molar average it will be mole fraction, and here the formula through which we can get our characteristic velocity for each individual cases.
exactly.
Now let's talk about the total flux.
Total flux is actually, as we have mentioned in the previous our presentation. Total flux is the summation of molecular flux as well as convective flux. Molecular flux also we have mentioned as diffusion, right?
Correct. So we have seen that molecular flux is transport property into gradient of driving force.
Exactly.
And we have now seen that convective flux is quantity per unit volume into characteristic velocity. The sum, when we'll sum this up, we'll get our total flux. One other formula of molecular flux that we have seen that when we try to increase the similarity between all the laws is that diffusivity into gradient of quantity per unit volume.
Exactly.
So that's how we'll get our total flux. Now moving on, here
let's just tabulate everything into the one picture as the type of transport phenomena to the total flux, molecular flux, and the convective flux.
Yeah.
For momentum, energy, and molar and mass, different total flux, molecular flux, and the convective flux are given.
Yeah, so similarly for energy, we denote, this is the generalized denotation of the total fluxes in each cases. For suppose momentum, it is pi, energy, it is E, mole, it is Na, and mass, this is Wa. So here pi yx, Ey, Nay, Way. These are the total fluxes that we these are the like terms from how we denote each term. Then we'll talk about molecular flux. For momentum, we know that minus mu dvx by dy, and when we try to make the similarity more similar to each other every term, then
we made it actually per unit volume, so the quantity per unit
we
volume
multiplied
is-
it and divided by rho. Then we got our thermal like momentum diffusivity. Then we have got nu. Then similarly for energy, mole, mass, this thing we have already like studied.
Discussed.
Now let's talk about convective part. So the convective part here will be rho into vx into vy. So basically what is it says, this vy is our characteristic velocity, and this is our quantity per unit volume. So here we have seen that this is quantity per unit volume into characteristic velocity. So in the table itself, it is quantity per unit volume and characteristic velocity. The quantity per unit volume we have derived in the earlier cases. Similarly for heat, for mole, and for mass.
Exactly.
Moving on. Now these are the fluxes we know, molar, molecular flux and convective flux. Now let's talk about the ratios. Now again when we will take ratio, we will get some dimensionless numbers. This time when we divide convective flux with molecular flux.
Exactly.
Just putting out the formulas.
Yeah, now just putting out the formulas as he mentioned. Here, the convective flux is quantity per unit volume into characteristic velocity upon diffusivity into gradient of quantity per unit volume.
Yeah.
So let's
break down the gradient of quantity per unit volume,
so that we can get some quantity for the dimensionless number.
So what is gradient of quantity per unit volume? Here everything like, what is gradient? It is the change per unit length or change at a specific point. So similarly, change of quantity per unit volume. So gradient of quantity per unit volume, that means quantity per unit volume is there, and what is its change per unit length per unit like point at two different points. So hence we like mentioned gradient of quantity per unit volume is difference in quantity per unit volume divided by characteristic length. So change in quantity per unit volume divided by length. That is, we will get quantity per unit volume per unit characteristic length. Now this is our equation B, this is our equation A. Just substitute it in equation A, then we'll get our ratios as quantity per unit volume into characteristic velocity, which is our convective flux, and we have changed a little bit in molecular flux, diffusivity into quantity per unit volume into characteristic length.
So we can say the quantity per unit volume get cancelled out. So finally we get the ratio of convective flux to the molecular flux as characteristic velocity into characteristic length divided by diffusivity.
Yeah, so this is the formula that you need to remember, which is the ratio of what will be the ratio of convective to molecular flux, which is we can say in notation form VCH into LCH by DAV, characteristic velocity into characteristic length divided by diffusivity. Moving on, so what we have studied till now, ratios. What ratios give ratios gives us dimensionless number. Here in this flux cases, when we took the ratio of convective to molecular, we get some dimensionless numbers. Now as we have told you, VCH into LCH by DAV in mass diffusivity case, and for energy diffusivity case we will get alpha. So when we will put the formula in their places, we will get our some dimensionless numbers which we call as Peclet number. Now let us discuss about the importance of the dimensionless number. We have already discussed this previously, like it is the ratio of two different quantities and it shows the dominance between the two quantities, which is flux in our case, convective to molecular flux. As mentioned here, if our Peclet number is less than 1, we will use the formulas for the molecular flux, and if it equals to 1, we will there is molecular flux as well as convective flux, and if the Peclet number is greater than 1, there is more dominance of convective flux. So this was our dimensionless number when we divide molecular flux and convective flux. When we took ratio of convective flux to molecular flux, and we get our Peclet number for heat transfer, Peclet number for mass transfer, and we also now know the significance of this dimensionless number.
Okay, now let's start with some numerical part.
so that we can understand more detail about the formulas and the relation between all the three laws and dimensionless number in detail. So our first question is, so show that the force per unit area can be interpreted as molecular flux. So we are doing this by comparing the units of both, like force per unit area and the momentum flux. So we all know that force per unit area has the units of Newton per meter square, and the Newton unit as kg, acceleration, which is meter per second square. So it's kg meter per second square upon meter square, and it overall become kg per meter second square. And momentum flux, we all know what flux actually is. Flux is anything per unit area dot second, which is for momentum case it will be momentum upon area per second. So it will be mass kg into meter per second upon meter square second. If it cancel out and we'll get kg per meter second square. Overall, we will get that a force upon area is equals to kg per meter second square, and the momentum flux m dot p upon time into area, we get kg per meter second square. Therefore, both of their units are same, so that we can say that force per unit area and momentum flux both are actually same. Now, let's start with our next question, which says a Newtonian fluid with viscosity of 50 centipoise is placed between the two parallel plates, separated by a distance of 8 mm. Each plate has a area of 2 meters square. The upper plate moves in a positive x direction with a velocity of 0.4 meter per second, while the lower plate is kept stationary. We have to calculate in part A the steady force applied to the upper plate. Part B, the fluid in part A is replaced with another Newtonian fluid of viscosity 5 centipoise. If the steady force applied to the upper plate is same as to that of part A, calculate the velocity of the upper plate. So, for part A, let's write the given thing, which is mu is equals to our viscosity is 50 centipoise, which is equals to 50 into 10 to the power minus 3 Pascal seconds, and y is given as 8 mm, and area of plates is given as 2 meters square. So our situation is we have two plates. Upper plate is moving with velocity of 0.4 meters per second, and lower plate is stationary, which means velocity is 0. And we have this distance between them y as 8 mm. So we will use Newton's law of viscosity, which says tau yx is equals to minus mu dvx by dy, which will 50 to 10 to the power minus 3 difference between the velocities from 4 minus 0 into distance between the plates, which is 8 into 10 to the power minus 3 meters. So we will get, and we know that already solved that momentum flux is equals to force upon area. The force upon area is equals to 50 into 0.4 divided by 8, which will be equal to 5 Newton. So answer for part A is 5 Newton. Now for part B, the fluid in part A is replaced with another fluid with viscosity of 5 centipoise. Simple. Like mu will be changed by 5 centipoise, which is equal to 5 into 10 raised to the power minus 3 parts per second. That's it. Nothing much will be changed. We have to just calculate the velocity if the force of the fluid remains same as the part A, which is 5 Newton. So F by A is equals to minus mu dvx by dy. Same, we will apply the Newton's law of viscosity. We will get 5 by 2 is equals to 10 to the power minus 3 weeks minus 0. Everything is same, just the viscosity has been changed and the force remains same. 8 into 10 to the power minus 3. So Vx we will get as 4 meter 4 meter per second. So the final answer for part A is 5 Newton, and for B is 4 meter per second. That's perfect. That answer. Next question says three parallel plates are separated by two fluids as shown in the figure. What should be the value of I2 so that to keep the middle plate stationary? If we considered right side as positive x direction, then the plate 1 moves in the negative x direction with the velocity of 1 meter per second. The fluid between the two plates, plate 1 and plate 2, is fluid B, which has its viscosity of 0.8 centipoise, and the distance between these two plates is Y2, which we need to find out. And the fluid between the second plate and third plate is fluid A, which has its viscosity of 1 centipoise, and the distance between these two plates is 5 centimeter. The third plate is moving with velocity of 2 meter per second in positive x direction, which is denoted by v1, and plate 1 is velocity is denoted by v2. Now we will solve this question with the help of Newton's law of viscosity. So, so Newton's law of viscosity says tau yx is equals to minus mu times dvx by dy, where tau xy for the first part, which is the fluid between the plate 1 and plate 2. For that, we will solve it as for part fluid B, tau yx is equals to 0.8 times 1 minus 1 plus minus 0 anything, because the middle fluid is supposed to be stationary by 2, and for fluid B, sorry, for fluid A, 1 centipoise into its velocity difference, which would be 0 minus 2 upon 5 centimeter. Now, we know that the flux moving in y direction would be same. Therefore, 0.8 minus 1 upon 5 10 raised to the power minus 3 on 10 raised to the power minus 2 is equals to 1 1 into 0 minus 2 upon 5 1 minus 2. Here I made a mistake. I read where it must be y2, and see where y2 comes out to be the 2 into 10 raised to the power minus 2 meter is equal to 2 centimeter. Here is our final answer, 4 centimeter. Next example, the steady rate of heat loss through a plain slab which has a surface area of 3 meter square and 7 centimeter thick is 72 watt. Determine the thermal conductivity of the slab if the temperature distribution of the slab is given by T is equals to 5x plus 10, where T is a temperature in degrees Celsius and x is the distance measured from the side of the slab in centimeter. We will solve this question by Fourier's law of heat conduction, where flux is equals to minus k times dt by dx, gradient of temperature. Now, this is a flux, which is rate per unit area. Mm, Let's note down the given thing. Given is area of the slab is 3 meter square, thickness is 7 centimeter, which is x, and rate is given by 72 watt. Now everything is given. Let's let's calculate the gradient of temperature dt by dx is equals to 5, and therefore on area is equals to minus k dt by dx, which will be 72 divided by 3 is equals to k times 5. So our thermal conductivity comes out to be 0.048 watt per meter degree Celsius. Let's verify our answer. Yes, it's correct. 0.48 watt per meter degree Celsius. Now, the next question is the inner and outer surface temperature of 20 centimeter thick brick wall are 30 degrees Celsius and minus 5 degrees Celsius, respectively. The surface area of the wall is 25 meters square. Determine the steady rate of heat loss through a wall if the thermal conductivity is 0.72 watt per meter Kelvin. Let's write the given thing. Given is the temperature of inner and outer surface of 20 centimeter thick brick wall. 20 centimeter thick wall is 30 degrees Celsius and minus 5 degrees Celsius, and its thermal conductivity is 0.72 watt per meter Kelvin. Now, this question is solved by Fourier's law of heat conduction, which is Qx is equals to minus k dt by dx. Qx is equals to 0.72 into the temperature difference will be 30 minus of minus 5 upon 20 into 10 raised to power minus 2, which is our thickness. So flux comes out to be Q upon the rate upon area. So Q upon 25 is equal to 0.72 into 30 minus 5 upon 20 into 10 raised to power minus 2. So rate comes out to be 13150 watt. This is our final answer. Let's verify it. Yeah, 3150 is our steady rate of heat loss through the wall. Next, energy is generated uniformly in a 6 centimeter thick wall. The steady state temperature distribution is given by T is equals to 145 plus 3000 Z minus 1500 Z square, where temperature is in degrees Celsius and Z is the distance measured from one side of the wall in meters. Determine the rate of heat generation per unit volume if the thermal conductivity of the wall is 15 watt per meter Kelvin. Now, to find the heat generated per unit volume denoted by capital G, we need to know the heat traveling through a plate of area A is from this side would be Qy, which is the heat flux, and from output it would be Qy plus delta y. Now we will apply the heat balance equation, which says input rate minus output plus generation minus consumption is equals to accumulation. Now we know there would no consumption of heat and no accumulation of heat. We need to find the generation. So input rate must be uh, Qy, which is equals to input rate upon area. So rate will be equal to flux into area. So Qya minus Qy plus delta Ya plus generation. Generation is heat generated will be equal to upon per unit volume. Our volume will be area into the thickness. So rate will be equal to generation into volume. So G will be equal to Qy plus delta Y minus Qy by delta Y, which came into the differential form. Therefore, heat generated per unit volume will be equal to dQy by dy. Now, from the Fourier's law of heat conduction, Qy is equals to minus k times dt by dy. Now, putting this value in this will get finally the heat generated per unit volume is equals to minus k d square t by dy square. Now, coming back to our question, we have temperature distribution as T is equals to 145 plus 3000 Z minus 1500 Z square, and we have to determine the heat generated per unit volume. We have uh, we we have derived the formula of heat generated per unit volume as G is equals to minus K d square T by dy square, which will for this case comes up to be because our thickness is in z direction. Therefore, dt by dz, single differentiation will be 3000 minus 1500 into 2z, and this will be dz square is equals to 1500 into 2. Now, putting this into our formula, G will be equal to 15 into 1500 into 2, which comes out to be 45,000 watt per meter square, which is 45 kilowatt per square, which is our final answer. Let's verify it. So, our
Heat generated per unit volume is 45 kilowatt per meter cube. Let's go to our next question, which says the steady state temperature distribution within a plane wall 1 meter thick with a thermal conductivity of 8 watt per meter Kelvin is measured as function of position as follows. This table is given for the temperature distribution with respect to Z, where Z is the distance measured from one side of the wall. Determine the uniform rate of energy generation per unit volume within the wall. Now, we have already calculated the formula of heat generation, which is minus k d square T by dy square, as the table given. We can write this in the difference form. As we have the table, we will table given. We have T, we have Y. We'll calculate the cumulative and its ratio, and then we will calculate the d square T by dy square in a tabulated form, so that we can take an average of this. So the difference is in this, in this, and difference of this delta y 0.1, 0.1, 0.1, 0.1, and we will take the ratio of these two. We'll get 158, 135, 110, 186, 162, and so on. We also know, according to the mathematics, delta square T upon delta y square will equal to delta T by delta y minus delta T by delta y1 y2 upon y2 minus y1, which for each case comes out to be minus 240, where the average of this will also come out to be minus 240. Therefore, delta square T by delta y square is equal to minus 240. And according to our formula, G will comes out to be minus 240 into 8, which will be 1920 watt per meter cube. 1920 watt per meter cube. Thank you. That's all for the numerical part.